Alright, in this video we're taking a look at how to draw Lewis structures for covalent compounds and how to show the transfer of electrons in ionic compounds. In order to determine what type of drawing you're going to need, you have to determine if you're working with an ionic bond or a covalent bond. The type of bond comes down to something called ionic character. Basically what you do is you take the electronegativity value of the elements that you're comparing and subtract them, and then you could take a look at this little scale right here and it'll tell you what type of bond you have. If the electronegativities are really close to each other, that's a covalent compound. Covalent means that they're sharing their electrons, in this case be pretty equally. If you have an ionic character of 0.3 to 1.7, that means that it's polar covalent. Still means that they're sharing electrons. It just means that whatever element has the higher electronegativity, like fluorine, maybe chlorine, is hogging the electrons, so they spend more time around one element than the others. And if the electronegativity difference is greater than 1.7, we say that it's ionic. And what happens in that case is because one element is so much stronger than the other, they're able to actually take the electrons away from the weaker atom, and they form a different type of bond. They don't share them. Okay? Now, if you don't have electronegativity values, there is a shortcut that we can use. Okay, what we say is that if you have two nonmetals together, then that is covalent. So covalent is two nonmetals coming together. Okay, so if I have any two of these up in the upper right hand side, let's say that I have oxygen and fluorine coming together, that make a covalent compound. Even hydrogen, even though hydrogen's way over here, that is a nonmetal. It does behave like the nonmetal. So H2O, for example, H, hydrogen and oxygen, that's a covalent compound, and that's water. Okay. For you to have an ionic compound, you need to have a metal or a polyatomic ion in there somewhere. So metal plus nonmetal, that would be an ionic compound. Okay. And the way it's written, whenever you have an ionic compound, the metal or the positive ion is written first. So, for example, table salt, NaCl. All you ever have to look at is that first one, because if there's a metal present, it's going to be the first one. We can see here that sodium is in the metals. It is an alkali metal. Therefore, this would be an ionic compound. So let's look at some examples of how to draw some of these. First thing you see is that we have this compound here, and it starts with carbon. So the first thing, we only have to look at that first one. We can see carbon is a nonmetal. So this is going to be covalent, so we can go ahead and draw the molecule out. Okay. So what we need to do when we do this, we need to determine a couple things. We need to figure out how many valence electrons this compound has. Basically, how many electrons are there in the outer shell of each of these elements. How many would each atom like to have in its outer shell? Bonding electrons, basically, whenever we compare these two, how many are going to have to pool together to make some extra bonds, and then what's left over. So let's start. Let's start with the valence electrons. What you do is you look and you find them on the periodic table. So the first one we're looking at is carbon. Okay, the shortcut is just to take a look at the number directly above the column that you're working with. So hydrogen would have one valence electron. Boron would have 3. Ignore the 1. This would have 4, 5, 6, 7, and 8 valence electrons. So it was carbon that we were concerned with first. We look up and we see that there's a 4 there. Therefore, we know that carbon has 4 valence electrons. And then we have another element, we have hydrogen. There's 2 of them, so it's going to be 2 times however many valence electrons that hydrogen has. And we can see that hydrogen's in group 1, therefore there's only 1 electron in the valence shell. So 4 from carbon plus 2, because there's 2 hydrogens, times the 1 valence electron it had. And then we also have a fluorine atom. We have actually 2 of them. So it's going to be 2 times however many valence electrons fluorine has. And if you look in the periodic table here, it's in group 17, giving it a total of 7 valence electrons. So 7. So we have 4 plus 2 times 1 plus 2 times 7. So this simplifies to 4 plus 2 plus 14. And this gives us a total of 20 valence electrons. There are 20 electrons that we have to work with. Okay. Well, the octet electrons that we need next, that tells us if carbon had every electron it wanted and hydrogen had every electron it wanted and fluorine was full, how many would be there? So the rule is that every atom wants 8. Okay, everything wants 8 except hydrogen wants 2, and group 13, which is basically just boron, wants 6. All others want 8. So it's only hydrogen or boron we're concerned with. We do have a hydrogen, so that's going to be a special case. Carbon wants 8. We have 2 hydrogens, and they each want 2. So 2 wanting 2 plus fluorine. It's not a special case. So 2 fluorines times the 8 that they want. 8 plus 4 plus 16. This will give us a total of 28 that we would like to have. Okay, so we have 20, we want 28. That means that we have to find a way to get 8 more by bonding. So you subtract this minus this, and that tells us that we have 8 that we have to share to make it look full. Now, electrons are always shared in pairs, so you never just share one electron. One line in a bond is equal to 2 individual electrons. So we're going to have 8 individual electrons that are going to be shared together, so that's going to give us 4 pairs. Okay? You just take this, divide by 2 to determine how many bonds that you will need. And then the lone pair of electrons, this is how many electrons that will be left over after we're finished bonding. So our total pool, we had 20 possible electrons to use. We're going to have to go ahead and use 8 of those in bonds. So 20 total, use 8 to make bonds, so 20 minus the 8 that we use tells us that we have 12 electrons to work with after we're done. Okay. So now we have all the information that we need. We're ready to go ahead and draw this molecule. So you need to find your central atom first. And the rule is it will always be carbon if carbon is present. It will never be hydrogen. So because there is a carbon, that means that my carbon atom goes in the middle. Now I just need to go ahead and disperse these others around it. So we'll have hydrogen, hydrogen, and then 2 fluorines. So as you can see, CH2, F2. Now we need to figure out how we can bond all these to our central atom. Well, we have 4 bonds that we're able to make based on our data. So 1, 2, 3, 4. Okay. Now we have 12 electrons that we have to place around individual atoms. Okay. This tells us how many extra dots we have to distribute. Keeping in mind that carbon wanted 8 electrons. We can go ahead and count, see how many it has right now. Remember, one line is equal to 2 electrons, so 2, 4, 6, 8. Carbon has 8, so it doesn't want any more of these leftover electrons. Hydrogen fills up at 2. It was one of those special cases. So each line counts for 2, so this hydrogen has 2, and this hydrogen has 2. So hydrogen is happy. If we take a look at fluorine, fluorine wants 8. But it only has 2. Each fluorine is only sharing 1 pair with carbon, so there's only 2 electrons in the valence shell right now. So we need to go ahead and show it having 8. So that would be 1, 2, 3, 4, 5, 6, plus the 2 it has gives it 8. And we've used 6 of our 12, and we have another fluorine, so we use the other 6, and we fill up the valence shell for fluorine. Now everybody's happy. We've used all 20 electrons that we had available, and this would be the correct Lewis structure for this compound. Okay. Now we're going to take a look at another compound here. Okay, so this time we see that we have MgO, magnesium oxide. And if we remember from the beginning here, whenever we have a metal and a nonmetal, this is known as an ionic bond. We can see that magnesium is a metal. In fact, it's an alkaline earth metal, so this is not going to bond. It's not going to share electrons. What it's actually do is transfer the electrons. So the way we show that is we show the dot diagram for each atom that enters into this bond. In this case, magnesium has 2 outer shell electrons because it is in group 2. And that's going to come together with oxygen, which has 6. And these electrons are going to actually transfer over to the oxygen atom here. So magnesium is going to become positively charged. By losing 2 electrons, you become positively charged. And oxygen, on the other hand, is going to receive these electrons, filling its valence shell, and gaining 2 electrons gives you a 2- charge. Adding electrons makes you negatively charged, losing electrons makes you positively charged, and we do have some energy released. All ionic bonds are exothermic. They give off energy. And finally, we have one more compound to deal with. In this case, we have nitrogen and oxygen, and we see that there's a negative charge on this. Might not be very clear, but this is negatively charged. Okay, so the whole compound has a charge on it. Well, nitrogen and oxygen are both nonmetals. That means that this is a covalent compound that we'll have to draw out. So we start by counting how many electrons are in the outer shell of this compound. Find nitrogen on the periodic table, and you'll see that it is in group 15, meaning that there are 5 electrons there. And we're going to have oxygen also, and we can see right now that there's 6. So 5 for nitrogen, 6 for oxygen. So I've got 1 nitrogen, so that's 5 valence electrons there, plus I have 3 oxygens that each have 6. Plus, this charge right here is in the valence shell. So since it's just a -1, that means that we have picked up 1 electron somewhere. There's 1 additional electron that we have in the valence shell. So the total number of electrons we have to work with here will just be 5 plus 18 is 23 plus 1 is 24. Okay. Octet. So we need to determine how many each atom would like to have. The only exceptions were hydrogen or boron. So everything here wants 8. So nitrogen wants 8. Plus I have 3 atoms of oxygen that each want 8. So this is going to be 4 8s, which is 32. Now notice we only used the negative charge when we were dealing with the valence electrons. This does not affect the octet electrons. To find the bonding electrons, you subtract the valence electrons from the octet, so 32 minus 24 is going to give you 8. Electrons are always shared in pairs, so half of that is 4. And what's going to be left over when we're done bonding? Well, we started with 24, used 8 of those to bond, so that gives us 24 minus 8, 16 left to distribute. So we determine what our central atom is. Well, in this case, it is going to be nitrogen. Okay, it's usually going to be your first one. It's the one that has the lowest electronegativity, and they're written in order of increasing electronegativity usually. So nitrogen is going to be our central atom, and we have 3 oxygens surrounding it. Okay. And I take a look here and I see that I have 4 bonds that I need to show, but I only have 3 atoms. So I'm going to have to go ahead and in one of these I'm going to have to double bond it. Okay, I can use double and triple bonds, no problem. Here I had to show a double bond. So I still have 16 electrons that I need to go ahead and distribute. And if I take a look, my nitrogen is fine, 2, 4, 6, 8. So it's only my oxygens that need more electrons. This one that's double bonded already has 4, 2, 4. So it just needs 5, 6, 7, 8. And the ones that are single bonded have 2 each. So they need 6 more. And if I total them all up, I see that I have 2, 4, 6, 8, 10, 12, 14, 16. That matches what I needed. Okay. Now this thing did have a charge on it. This was a ion. This is the nitrate ion. So it does have a minus charge. Now, because we did have an option for where we made the double bond, we could have put it here or we could have put it here, we actually have to show it in all the locations that it could have been. This is known as a resonance structure. Okay. So the way we deal with this is, because there were 3 different places we had the option of showing this bond, we're just going to rotate the bond around twice and show it in all the different places. And once you've drawn the first one, it's easy to go ahead and just show both of them, because it's just literally taking it and rotating it around. And this is still a negative ion, and then the last one. Running out of room this time. It's going to be on the right. And we just fill in our electrons. And this would be the complete Lewis structure, including the resonance structures for the nitrate ion.